Get started. So, briefly, this is the last lecture. I'm going to get through all of chapter 11, and I think there'll be some time to talk a little bit about chapter 12, which basically describes how it is that we move from DNA to protein. So how do we construct proteins from the DNA blueprint? There will be a quiz this week, and it will include some content from Elephants on Acid and lecture content, unless you're a part of the online section, in which case it's just going to be over lecture content. So our final is going to be in here Friday, so day after tomorrow, at 8 o'clock, I believe. Is that correct? It's going to go from 8 till 10. And unfortunately, there's going to be a hard stop at 10 because I have a second final that I'm giving that day starting at 10:15. But I don't believe it'll take you the full 2 hours. It won't be that lengthy. I started writing it yesterday. So I completed the comprehensive portion of it. And what I did was I took like 5 items from the first like 10 chapters that we went over. And I really tried to focus on major concepts, not like minutia. So for example, I didn't ask you like how many ATP are created within a particular section of cellular respiration. It was more like, which of the following is used to completely oxidize pyruvate to create a whole bunch of electron carriers type stuff. So much more conceptual, okay? So as you're moving through content, as you're studying, I would worry less about detail and more about concept. Does that make sense? Okay. The non-comprehensive portion of it will be very different. So that is going to be a lot more detail-oriented. So you can expect this diagram to show up somewhere on the exam, okay, for the non-comprehensive portion. Any questions? Yeah?
Are previous exams those are good to study from?
I believe so.
Okay.
Yeah.
Is there going to be a lot of similarity between them or no?
So I didn't take any questions directly from
Okay.
previous exams and put them on this exam. I rewrote all new items.
And are you going to be dropping our lowest regular test grade?
I will. And lowest quiz grade. Yeah, Sophia.
So like, how many diagrams will there be? Like, will there be like a photo system?
So for the comprehensive part, there won't be any diagrams.
Okay.
Just for the non-comprehensive part. And I don't know how many, because I haven't started writing the non-comprehensive part
Okay.
yet. My guess is, I think what I would like to do for the non-comprehensive part is have about 35 multiple choice items, have 5 short answer items, of which you'll answer 4 like normal, and then have 1 long answer item, which might be 1 long diagram, kind of like what I'm drawing up on the board right now.
Okay.
So that would be a 10-point item. Each of the short answers would be 5 points, and then multiple choice 4 points. Carly.
So you said that for the comprehensive part, you said it's just 5 questions, and then the rest
From
of
each
it-
chapter?
Each chapter?
Yeah.
Okay. I was confused. I was like, whoa, that's very confusing.
Yeah, not very many points. That was the case. Okay, so we left off here talking about DNA replication. Let's review this diagram really quickly, and then we're going to finish up with DNA replication. Talk a little bit about mutation. Okay, so remember, the DNA molecule consists of 2 sides, right? It has 2 complementary strands. And when DNA replication is occurring, it's occurring in a single direction. In this case, it's occurring from the left to the right, along the lagging, or excuse me, along the leading strand. What does that mean about this end? Is this 3' or 5'?
3.
This is 3' end, exactly right. Which means that it has a sugar sticking off the end of it, right? And the 5' end, which would be down here, has the phosphate sticking off of it. So this is 3', and this is 5'. Which means that the complementary strand has the opposite orientation, correct? So that means that this has to be 5', and this has to be 3'. Now that tedium has some value and some importance when we start talking about lagging strand replication. Because the overall direction of lagging strand replication has to be the same as the leading strand replication, but it's going to be occurring in sections that move in the opposite direction, which will make more sense in a few minutes, I promise. Okay, so let's start from the beginning of DNA replication. Which enzyme is it that takes the DNA molecule and unwinds and unzips it? Helicase, exactly right. So helicase's job is to bind to a specific region of the DNA and unwind and unzip it. And it's always going to move along the leading strand from the 3' to the 5', from 3' to 5' direction. Okay? Now, we know that the bond that's holding complementary strands of DNA together is a hydrogen bond, right? Which those form spontaneously, and they're a product of two partially charged either atoms or molecules that are holding things together, right? So if helicase unwinds and unzips the DNA molecule, if we don't do anything downstream from the unzipping, then it's just going to spontaneously connect back up. And so we have to apply something to keep that from happening. And what is that? Yeah, the single strand stabilizing proteins. Those are going to keep the two complementary strands apart from one another. Okay, so in order to actually start replication, we have to apply a primer. And do you remember which enzyme applies the primer? Primase, yeah, it's not a very creative name at all, is it? Primase applies that primer. And that primer consists of what? DNA or RNA nucleotides? RNA nucleotides, yeah. So this is RNA. Okay, and then another enzyme comes along and it starts applying DNA nucleotides as a complementary strand, right? Following right behind helicase. And what was that enzyme called? DNA polymerase 3. Exactly right. Okay, and so then helicase is going to continue to unwind and unzip in this direction, and DNA polymerase 3 is just going to follow right behind it and continue to apply DNA nucleotides, right, making a long complementary strand. But we need to come back here and replace that RNA primer with some DNA. And what does that? DNA polymerase 1. Comes back here and it replaces that RNA primer with DNA nucleotides. And I'm just going to draw it above the primer like that. So you guys, the most difficult part about this is just remembering who does what, right? And really the only two that are very difficult to remember are the polymerase ones, because they don't really correspond to, or the name doesn't really correspond to the thing that they're actually doing, right? So just remember, the DNA polymerase 3 builds the complementary strand, and polymerase 1 just replaces the primer with DNA nucleotides, okay? So that's leading strand replication. Are there any questions about that? Okay, so here's my last question to you. As DNA polymerase builds the builds the complementary strand, what is this end? Is that a 3 or a 5' end? 5' end, yeah. This has to be a 5' end down here and a 3' end down here. Because remember, what's going to happen is this, leading strand acts as a template, right? And ultimately it's going to come apart and it's going to have a new complementary strand attached to it. What that means is that new complementary strand has to have an opposite orientation to the leading strand. So since down here the leading strand started with the 3', the complementary strand has to start with the 5'. So when DNA polymerase 3 builds DNA, it's building it from 5' to 3', but it's reading it from 3' to 5'. Okay? So the reading direction and the building direction are flip-flopped. Yeah, Sophia?
But, so, why does it stop, like, why does the 5 stop right there at primer on, like, at the primer?
That's just the first place where we have a new complementary strand being built. Remember, upstream from this, we're going to have other DNA polymerases working, and ultimately it's going to be one long new contiguous strand. In fact, if we were to draw, like, so I'm going to get a drink really quickly. if we were to draw that chromosome that's being replicated right now, what it would really look like, I should draw like this, is this. Where we have a whole bunch of DNA replication that's working simultaneously. And that section right there might just be this section right here. So there's some other DNA polymerase and replication going on upstream from it. And ultimately, it's all going to become contiguous. And this whole top strand is going to separate with the new complementary strand, and that bottom one's going to do the same thing.
Okay. So
Okay.
like the are we gonna get to the bottom of that?
We are.
Okay, cool.
It's just a little bit more complex, and so
Okay.
we're taking our time. Yeah, Carly.
Kind of conceptually a little bit similar to how prokaryote cells replicate their DNA, where they have that, they have the
Replication loop.
replication loop.
It is similar, yep. And they have similar mechanics that accomplish that, or similar enzymes that accomplish it. Okay, so are there questions about leading strand replication? Okay, so here's the problem with lagging strand replication. Remember, DNA polymerase 3 always reads from 3' to 5'. And helicase isn't opening up anything else in that direction, right? So what that means is if DNA polymerase 3 is going to read from 3' to 5', it's going to start right here, right? Because this would be a 3' end, and it would read in that direction. But it gets to a point where it has to stop, because helicase isn't opening this stuff up over here. And so it could really only replicate that much of the DNA. Does that make sense? Because it has to read 3' to 5'. So what happens is, it replicates a little bit, and then it waits for helicase to open up more. And then once it's opened up more, it then replicates that little bit from there back down to that first section that it replicated. And then helicase will open up more down here, and it'll replicate that back down to this direct, to that second segment that was created. Does that kind of make sense? Okay, so fundamentally, it's the same process. And let's say that we're going to create our first segment right here. What happens is an RNA primer is applied by which protein again? Primase. Exactly right. Primase comes along, and it applies an RNA primer. So DNA polymerase can come along, and it can attach to that primer, and then create a new complementary strand. In which direction is it going to be creating it in? To the right or to the left? It has to be to the left, you guys, right? Because it's going from 3' to 5'. So it creates a strand in that direction.
So, okay.
And which enzyme does that? DNA polymerase 3, exactly right.
Sort of like the same helicase is working for both.
It's opening up both the leading and the lagging strands, but lagging strand replication just occurs in discrete units. Okay, so after this had happened with leading strand replication, what was the next thing to happen? What did we do next? Something with this. Yeah, we had to replace the primer. So we came back and we replaced the primer. And what's the enzyme that does that? Polymerase 1, right? Okay. Now, this fragment right here, from its beginning to its end, is called an Okazaki fragment. Okazaki. Okazaki. Okay, so that's the first Okazaki fragment that's been created. What happens then is after helicase opens up some more real estate on the lagging strand, then another thing, or primase comes along again, and it lays down a primer. DNA polymerase 3 comes along, grows out that primer until it gets to right here. DNA polymerase 1 comes along and replaces that RNA primer with DNA nucleotides. Yep.
So when you say replace, it would just like, would it
Pull.
push back the primer and like connect to the DNA strand right there?
Yeah, it physically pulls the RNA nucleotides off and it replaces them with DNA nucleotides. Yep.
Could you like, I don't wanna be a bother,
Uh-huh.
could you like write down the steps of that?
Yeah, you bet. I sure will.
Thanks.
So this would be the second Okazaki fragment. Okay, so steps, and we'll call this lagging strand replication. So step number 1 is for primase to apply an RNA primer. Then DNA polymerase 3 grows the primer out. Which makes a complementary strand of DNA. Then DNA polymerase 1 replaces RNA nucleotides